So if we just remind ourselves of what integration is, it's kind of like saying, here's a function that's going to tell us the slope values of another function. So if we just consider the graph of negative x squared plus 2x plus 4, that function's y values will tell us the slope values on some other function. And so the problem that we're going to look at today is, what is the equation of the curve that's going to pass through some point given we know the slope values of that function? That is really what integration with conditions is all about. So we have a look at this same parabola. What we can do to find this function, okay, after kind of visually seeing that y values on that graph map the slope on the other function, how we determine that function is by taking the antiderivative, which gives us our function with a plus c at the end. Now we know that if we add a constant to the end of a function, that is not going to change the rate of change. It's not going to influence the rate of change. And so that's kind of just like a slider. And you can kind of think of it as just sliding the graph until it perfectly goes through the dot. Okay, and in this circumstance, the c value would be -1. And you can kind of do a little gut check here and see that, well, do these slope values still map this curve? And with a little programming, you can kind of verify this for yourself. So here's our question. It says, determine the equation of the curve whose gradient is given by this function. So this function will tell us the slope values on some other function, and it passes through the point, this coordinate point here. Now just to iterate, this is when x is equal to 0 and y is equal to 1. That's what that coordinate point is telling us there. Now I'm going to have to use my methods of integration here, and so I just don't want to bugger anything up. And so if I'm at negative cos and I take the antiderivative or the integral, I'm going to get to negative sine. So here, if I've got a dy dx equal to this thing, when I integrate, okay, and I'm going to add my dx for notation there. When I integrate this function, what I'm going to get here is I'm going to have negative sine of 2x divided by that 2 scalar plus x squared over 2 plus c. Okay, that's what I'm going to get there. And this plus c value is going to be given, that is going to be given by this additional piece of information here. Okay, but let's not get ahead of ourselves. Let's clean this thing up. So here we're going to have y is equal to -1/2 sine of 2x plus x squared on 2 plus c. And you can do a little gut check here. You can differentiate what you've got here. So if you differentiated -1/2 of sine of 2x plus x squared on 2 plus c, you should get back to your gradient function. Okay, when you differentiate, you should get back there. And what we're doing here is we're just saying, hey, we know some additional piece of information, so that is going to help us solve for c here. So we're going to use a piece of information, which is x being equal to 0, y being equal to 1, to find c. Okay, and so we can simplify this a little bit here. First term I'm going to look at is my sine. If you forget this stuff, draw yourself a little unit circle. Sine is the y-axis, cos is the x-axis. Sine of 0, 0 radians around, that's going to be equal to 0. I might do this in a different color here, in a purple. It's going to be 0 on the y-axis, or on the sine axis. So this value here, sine of 0, is going to be equal to 0. Alright. Okay, taking this one step further here, I can say I've got 1 is equal to -1/2 times by 0 plus c. So really that's saying that c is equal to 1, and therefore I've got a function which is -1/2 sine of 2x plus x squared on 2 plus 1. That is the function which is the curve that passes through this point here, passes through that point there, and its slopes are given by that. And so we can do a little bit of a verification here. This is our function here that tells us slope values, and so if we just do a little bit of interpreting before we open it up, we can see here we've got negative y values, so we can expect the slope to be going down, or this graph should be decreasing. Then it gets to this point here, this point right there, and then we can expect the slopes to start increasing. And so that's what the function should look like. So it decreases, and then right at that point there, if we actually zoom up on it, right at this point here, okay, it's flat, but then the graph starts to increase. And as it should, because, well, this red one is telling us the slope values of the blue one. And so anyway, if we play the slider here, we can see that at some value for c, it's got to go through the coordinate 0, 1. Okay, and it actually just so happens that it's on the exact point of 1, that occurs. And so that's our function there, which is very nice. Now these problems do apply with kinematics, or that is looking at movement. And so imagine you've just got 3 particles, and you know the velocity of all 3 particles. So just to remind ourselves, if we've got negative velocity, that means that we're moving to the left, and positive velocity, we're moving to the right. So we've got negative velocity, so it's moving to the left pretty quickly, and then it slows up, then it starts to subtly move to the right, and then subtly moved to the left, and then it starts to move to the right very quickly. And all 3 particles are moving at the exact same speed. Now the problem here is that sure, we know the speed, or we know the velocity of the particles, but we don't know where they are positioned in space with respect to some fixed origin. Finding that out is going to take a bit of additional information. Okay, and so if we take the integral of our velocity graph, we get a displacement function, and it's going to have a plus c constant at the end, because we know plus c has got no rate of change. So really, in order to find the exact displacement of a specific particle within context, we need more information. And so if I were to say straight up that I know for a fact that the particle was originally positioned 4 meters to the left, you would look and you'd go, okay, it's the purple one. But without that information, if you only knew the speed or the velocity, you could have an infinite set of particles that could be doing this, okay, with respect to where they are positioned to a fixed origin, okay, because no matter how you draw it, all of the slope values will be the same, okay, which is what the velocity graph is telling us about the displacement graphs. It tells us how the displacement is changing. And so I've picked an arbitrary amount here, which is just 3 particles. There's an infinite set, okay, because there's an infinite number of c values. But if you've got that specific initial condition, you can be sure to say that it is the purple one that we're after. Just to give a small little recap of a spiel, dVA, okay, that's our displacement, velocity, and acceleration. And we remember that if we differentiate, we go down the way. So differentiate. So if you've got displacement, you differentiate it, you get velocity. Or in other words, velocity describes how displacement is changing. When we take an antiderivative, we can go the other way. So if you're at velocity and you want to find displacement, you take the antiderivative, or you take the integral. Okay, let's have a look at these questions here. So I've got some car is moving and the velocity can be measured by a velocity function, great, for the first 6 seconds of the journey. Part A is saying, determine when the particle is first at rest. Alright, well let's see if we can do that. Okay, just to reiterate this point here, that means determine when the car is just chilling, or when it's got no speed. So that's when v of t is equal to 0. So we can substitute that in for v of t and say 0 is equal to negative sine of 2t plus 1. And we can rearrange and solve this here. Alright, I know that sine of t, actually I'm going to use a different variable here, sine of theta, and cos of theta. I know sine of theta would be equal to 1 at pi on 2 radians. Okay, so if I just do a little bit of substituting here, if I just say let 2t equal theta, I know that sine of theta is equal to 1 when theta is equal to pi on 2. So therefore, 2t is equal to pi on 2. And if you're solving for t here, you can just divide by 2 and you get pi on 4. So this is when the car... Okay, and so we can verify that later on. Now there would be multiple solutions for when the car is at a standstill, okay, but they would be, theta would have to be plus 2 more pi, so you could get more solutions. You could say 5 pi on 2, 9 pi on 2, etc, etc, but we were interested in the first one, so there was no point going past the first solution there. Now we'll have a look at B. Okay, B saying determine the equation for the displacement of the car if it was known that the initial position was 1 meter to the right. So we've got some kind of a problem here. This is really saying d of 0 is equal to 1. Or in other words, on our displacement function, this is a coordinate. Therefore, that coordinate exists on our displacement function. And the displacement function can be given by the antiderivative of the velocity function. So we go ahead and solve for that. Okay, so we can take the antiderivative there, and we get a solution for d of t, where we've got some plus c value, and we're going to use our initial condition. Okay, we're going to use our initial condition, and that was that 0, 1 was a coordinate that we can sub in. So in other words, d of t, d of 0 is equal to 1. So we can substitute that in. We can say, well, 0 is equal to cos of 2 times 0, because t is equal to 0, over 2 plus 0 plus c. And with a little bit of help from the unit circle here, we know sine there, cos there, this here, cos of 0, if you go around 0 radians, you're at cos being equal to 1. So this thing here is equal to 1. And we can just really finish this off here. Oh, it's not equal to 0, sorry, it's equal to 1. It's equal to 1, because d of t, or d of 0 is equal to 1. My apologies. Plus 0 plus c, take away a half from either side. You get a half is equal to c. So therefore, you've got a function. Okay, and so this would be the function. Okay, the displacement function. And so we can do a little bit more verifying here on our friend Desmos. Okay, we'll get rid of that initially. So the first thing I want to look at is where was the first point of rest. The first point of rest was at t being equal to pi on 4. So I'm just going to go in and see if I can solve for that. And I'm going to change my x-axis here to be in terms of pi, not, and I might say pi on 4 instead. And I can see that it indeed was first at rest pi on 4, at t being equal to pi on 4. Okay, nice. So I'll go and change that. So I'll change that back to just being in a step of 1 rather than in steps of pi. And here I might zoom in here. And so here I can see, here's the velocity graph for the first 6 seconds. It's always got a positive gradient. So whatever my function is going to look like, it's always going to be increasing for the first 6 seconds. Okay, so it's just going to be going up and up and up and up and up. Let's see what it looks like. Okay, so the slope values is always going to be increasing. And we can see that on this graph we've got our plus c constant there. And if we were to move the value of c up and down, we can do that, and it's going to pass through at exactly a half. So if we change it to 0.5, that is the graph that we want, where the slope is given by the velocity function, and it goes through exactly there, which is what we get. So that's always nice to check.